Okay, and the next speaker is Daniel Kondys. He's a FPGA researcher and developer at the Czech Education and Scientific Network Institution. He focuses on high-speed FPGA-based networking and hardware accelerator, co-developing the open-source network development kit, NDK, which is a framework for building high-performance network application on FPGA and smart NICs at speed up to 400 G, which he talked already about last year. So this year, he'll dive into high-throughput network monitoring pipelines. And welcome back.
Hello, everyone. Thank you for the introduction, Filberto. It's nice to be back. Yeah, so last year I've been here presenting about the network development kit, which is an open source framework for FPGAs that is focused mainly for network applications. I presented some example applications that we have. Now I'm going to speak about one particular application, and that is network monitoring. So first, I will start with some introduction and recap from last year, what the NDK framework is about, and then I will dive into the network monitoring, how it works as a whole, and then what specifically we do in the FPGA to accelerate it. Because when we are talking about high throughput network monitoring, we usually mean like 100, 400 gigabits per second. Okay, so a little introduction. The NDK framework is developed and maintained mainly by Sysnet, which is a non-profit organization in the Czech Republic. Mostly, its services consider internet access and internet services. It has also a big footprint in research and education. And now about the NDK framework. We have two repositories. One is the NDK FPGA, which has most of the FPGA modules, build system, verifications, and everything for building the FPGA designs. And then we have another repository for software that contains drivers, some software tools, and many other things. Now, I know that this was a little abstract, so I tried to explain the NDK framework on this picture. Let's imagine that you want to write an application that will process network packets in some way, and you have a lot of money, so you can buy a very expensive smart NIC with an FPGA. You have some SFP cages where you connect to the internet. You have a PCI connector to connect to the PC or server. And then you're left with many interfaces and stuff you need to take care of before you actually start writing what you want to do in the FPGA. So that's basically what the NDK is about. It provides these helpful blocks that just provide the interfaces to the application over here. So it's just like one file, one entity, where you have interfaces that where you received packets from the internet, where you can transmit packets back to the internet. You can communicate with the external memories, send stuff to the software, etc. So it basically just makes the developer's life easier. Now, about network monitoring, it is the main application for Sysnet that is behind the NDK framework itself. And when I say network monitoring, it basically means to capture the communication of where one entity in one network communicated with another entity in another network. Right. So in case of our network, the SysNet network, this is a little older picture, but if you look at these blue boxes, these are the monitoring probes that represent the lines which we tap into and monitor the traffic. So we always monitor what goes in and out of our network. We don't really care about what goes inside. At least it's not part of what our department does. We just monitor what goes in and out. Okay, so I have reduced the network monitoring problem into 3 steps. The first part of it is to somehow copy the data that are going from one network to another somehow. So we tap the lines, clone the traffic. That means network packets. And important note, we need both directions of the communications because most of the communication is request response. So it would be not ideal if we had just requests or responses. So we get the network packets, then we have something we call the monitoring probe that does some kind of processing on the packets and outputs network flows, which is a record of a couple of data I will show you in a second. It's just one record for the whole communication. So you don't have like many packets and many bytes of data that will be analyzed. You just have one record, a couple of bytes of data per each communication. And these network flows are then collected and redistributed to some storages, some output plugins for detection systems, and whatever is needed. To imagine what the monitoring probe is, or what it consists of, it's basically a server with an FPGA SmartNIC, in our case, plugged in, some Linux and Linux OS is installed there with the necessary drivers, and then there's the IPFix probe software, which actually does the packet processing, does the aggregation of the packets into flows. And how does a flow or flow record look like? It has these and sometimes more values. The first 5 on the left side, they are the identifiers of each flow. So you know which source communicated with which destination and using which protocol. And then you have the data that is gradually updated. You have timestamp of the first packet. You have timestamp of the last arrived packet, so you know how long the communication took. You have the amount of bytes that were transferred and how many packets was it. You can have these values for one direction and the other, but it's always a part of a single record. Right. So what we actually do in the FPGA for network monitoring, such as described.
We use it for packet processing, pre-processing, so the actual aggregation of the packets into flows is done in software, but in the FPGA we help it by providing timestamps. We provide parsing the protocol headers that are in each packet, and we also distribute the traffic into multiple queues, so the processor can utilize the many cores it has available. And we can also filter out some traffic of interest, perhaps some traffic that we are not allowed to monitor as well. So that is it in a nutshell. Now, how it works in the FPGA. The timestamping, we have a special module for generating timestamps, the TSU, timestamping unit. This unit is basically an advanced counter, which is synchronized by a software daemon that runs on the server and makes corrections if it drifts too much. So yes, it's the timestamp unit generates the timestamps according to the system time on the server. The timestamps are then sent to the network module, so each packet straight as it arrives gets assigned a timestamp, and the timestamps are also sent to the application in case the user would like to use it in some way. So this is the network module I showed previously. You can see it has a special timestamp interface. So when a packet arrives on the interface over here, it gets processed by some very smart logic, and the timestamp gets assigned to it by being sent on this bus on the bus for metadata that are transmitted with each packet. So there's not only the timestamp, there's also the interface identifier on which the packet arrived. There's also the length of the packet, if there were any errors detected when receiving the packet, and so on. All right, so one thing to note here, we have, you can notice these MFB and MVB buses. These are our special buses, which we have developed, or the concept of which we have developed quite a long time ago now, because we wanted to have some common interface, not to get stuck in with one FPGA vendor. So normally there's in the network module there is some sort of hard IP block for Ethernet from Xilinx, AMD or Altera. It has its own interface, so we convert it to our MFB. MFB stands for multi-frame bus, so this means we can actually stack multiple packets in each word of. So we can process multiple packets in each clock cycle, and I want to talk about this a little in this slide, because scaling beyond 100 gigabits per second requires either a very high frequency of the whole design or very wide buses. And I guess at least the older versions that were available when we were considering this were insufficient, and scaling was not very good. We came up with the multi-frame bus, which, well, like the current implementations, basically makes it possible to split the bus into multiple segments, in which you can say a packet starts here, a packet ends here, a packet starts here, a packet ends here, and so on. So you can, so in each segment you can have like this identifier that a packet, at least a part of packet is there. So that is the general idea behind this. If anyone is interested about this concept, you can talk to me about this after, or check out this very good paper written on it. But I will I will move on for now. So we have the packet, the timestamp, interface number, and some other meta information going from the network module to the application. And in the application, we have the other components that take care of the packet parsing, parsing packet headers, traffic filtering, and distribution to queues. There is, so, okay. Yeah, so when we have over here two of these pipelines, that is because one is for each port. And as I said, we want to have the packets of one communication. Oh, maybe I didn't say that. You want to have packets for the same communication for both sides, for both directions of the communication on the same queue. So it's easier for the processor to process it. You can have it on, it's better for the cache and everything. Right, so that's why we have like a redirection module crossbar that can redirect the packets as needed. Right. So let's begin with the packet parsing, packet header parsing. This is actually a really good design of a parser which can process multiple packets in each clock cycle. As I said, the interface is MFB, so we can have like four packets in each clock cycle, and we need to be able to extract as many headers in each clock cycle. So we have like a staged pipeline. In each stage, we have multiple simple processing blocks that are dedicated for special protocol. I mean, special just for specific protocol, and we can actually chain these blocks in whichever order we want to. We can, of course, have multiple VLANs to parse. We can have multiple MPLS headers, IPv6 also. So as you can see, this design scales well into the protocol. And the amount of supported protocols, as well as the traffic, the speed of the design. This is just the text for it. You can skip this for now. So this is how the inside of each protocol, the simple protocol analyzer block looks like. There's some command block that looks at the offset from the start of the packet, and analyzes if the offset has been reached. If it has, then it extracts the protocol bytes and sends it to specific protocol logic block that extracts the necessary information and outputs the next offset to the next pipeline stage. Then we have a packet filter. So when we imagine a packet filter, what we do is we define that this kind of packets cannot be transmitted. So the type of the packets is identified by a key. The key can be something like VLAN TCI, IP address, port number, etc. And if we want to have more actions than just to discard these packets, we can define them in a secondary memory, because the keys, the identifiers of the traffic that we want to perform actions on, is stored in a TCAM. So when the match data come in, they are compared inside the TCAM, and if they are matched, if they match one of the records, the address of the record is output from the TCAM. It addresses an action in the BRAM, and then the action is output. And the last part of it is the queue distribution, or receive side scaling, which is about sending related packets onto the same queues, as I said before. It consists of, well, 3 main blocks. We create a vector which identifies the flow. We hash it, and then we look inside, look up in a table onto which queue or channel to send it to. And at the end of the pipeline, there is the data export module. So this is where we drop packets that were marked so by the filter. We prepend the metadata that were processed in the blocks before, such as the parsed headers and timestamps and so on. We can also trim the packet if needed, and then we send it to software through the DMA. Okay, so I have talked about network monitoring, how it works as a whole, and what we do in the FPGA, the parse, filter, and distribute pipeline. I've mentioned the multi-buses that we use to scale the throughput. And unfortunately, even though the NDK framework is open source, this design is not. It is proprietary for SESnet. It's not even sold or anything. So you can find some examples with our partner, or also at our GitHub. Thank you for your attention.
Do you have any questions? One there.
Hello, Martin from Silicom here. Just a question about these segmented Mac bus that you had made your own standard for. Because I was considering this and what about Axie and Avalon and stuff like that? don't they have a segmented part for their standard?
Yes,
is that a new thing or is that an old thing?
They do now, but
do now, okay.
when we were actually creating this concept, I believe there was nothing like it. So that's why we came up with it.
Okay.
Can you hear me? Oh. Thank you for the presentation. But regarding the timestamp, you said that the timestamp mechanism communicates with the server using a software daemon. Where does this reside? Is it a bare metal application or a Linux application, or is it inside the FPGA itself?
Can you repeat the question? What exactly are you asking?
I don't know if you want to try to switch microphone. Let's see if that works.
Yeah, we have a timestamping unit in the FPGA, which is synchronized from the software daemon.
Yeah. So you said that the FPGA syncs up with the server to say like, oh, okay, this is the time. Right now, like maybe GST time or GPS time, whatever it is, on the server.
Yes.
Now, how is it, you said that there's a software daemon running, is it running on the FPGA? Or is
No, on the server.
On the server.
Yeah.
So, is there, like, how is the server communicating with the FPGA? Is it a bare metal application communication or a
yeah,
Yocto-based application?
There's we have a special bus for accessing registers in the FPGA to write and read data. So it just reads the data from the timestamp unit, checks if it's okay or if it needs to be corrected, and if it does need to be corrected, it writes new value into a register, and the timestamp unit will take it.
Nice. Thank you.
And yeah, first of all, thank you for the presentation. It's very interesting. But my question is about the filtering and how the TCAM concept helps with the lookup.
Once again?
Yeah, so you mentioned the TCAM
yes.
RAM that's being used for, and you mentioned that each bit can store either of the three
yes.
possible values. Can you please explain a little bit more how this works?
Okay, so I am not able to explain it like really in depth because the concept of TCAM inside the FPGA is not something I've personally dealt with. But the thing is that the power of TCAM is that yes, it has these three states that are possible to match, and hence you can apply masks. So you can mask like IP address prefixes and stuff like that. So that's what it's used for. Sorry, I can't explain more in depth.
It's implemented inside the FPGA, right?
Yes.
Okay, thank you.
Thanks. Do you have any other questions? Okay, I don't see, so I think we can thank the speaker again.
Thank you.